Okay, so next we talk about the student decision. So what decision can we have? Uh, for undergraduate student, actually, in China, so we do not, frankly speaking, we do not actually have much choice here uh, because a minimum requirement is a master or PhD student for a design house. So many undergraduate students can only go to the how to say it's a semiconductor fact. It's actually it's an industry. It's an industry to so what is the nature of the the job? The job is I think most of the job is to for example to go to the how to say it's a manufacturing, sorry, it's a manufacturing flow. Yeah, so mo most of students can go to side for example uh to, to study to learn to study the usage of some manufacturing equipment, yeah, or to collect data from the force testing, something like that. It's not really a analog circuit design. Yeah. So actually, I believe in the future, so more and more students have to pursue the master or PhD degree before they can real go into the design house. Yeah. So what can we choose after this program? Assuming we have maybe have a higher degree. So the first one, yeah, the first one is which is also a very high salary type job is an analog mixed signal design. So we design something like amplifier, actually open, right? Open and reference. So with reference is a high precision reference for for example the mirror, right? The current mirror or some the the temperature sensor, right? And also ADC and DAC voice data, analog to digital converter and digital to analog converter. So these circuits are very hard to design. Yeah. And also we have to understand each specification before we go to the interview. Yeah. During the interview, the expert will ask many yeah specs. Yeah. For example, during your master or PhD studies, so what spec have you got? For example, for amplifier, what is the near DC gain? How about the gain bandwidth trail? How can you extend? How can you extend this limit? And for example, for the reference, so how accuracy of the current mirror, and how about the temperature can vary the accuracy of the reference. For ADC and DAC, so they are too many to discuss. Yeah. So for example, the noise and the quantization error, and also the how many stage you are using for example for the pipeline, and also what topology, for example, delta sigma or something like that. So what topology you prefer for a specific application. Yeah. So you have to answer quickly. So what is the trade-off between each uh for each topology, for example, for the flash ADC, it's preferred when the speed is your concern, right? However, the quantization error is large and is also very power and area consuming, right? So how can you improve it? So you can say you desire you have other choice like pipeline pipeline structure and also oversampling structure, and you have to spec. So what is the proof and con of all this topology, and why do you think some topology is quite suitable for the for some real scenario the expert give you, right? Okay, so the next one is the RFIC. So this is radio frequency IC and the community circuit. The first one is LNA, so what is that is also is actually a low noise amplifier. So what is the difference between LNA and the amplifier here? Okay, so the amplifier here is actually more likely to refer to a open operational amplifier. LNA here is the first stage of our transceiver. Actually receiver, the first stage of the receiver. Yeah. Its main role is to amplify rather small signal from the free space, like from the other antenna. Uh, the antenna transmit something, the signal, right? Uh, because the high loss of the free space, the signal amplitude before entering the LNA here is rather weak. So the LNA here is not operating like operational amplifier. It's more likely to act like a high frequency amplifier to boost the voltage swing of the rather small signal. Yeah. So what is the typical uh, swing input swing for this LNA? The power is smaller than minus 20 dB actually for a real scenario, or even worse if the signal is transmitted by the how to say the uh airspace, right? Airspace. Yeah. So actually the LNA is very highly sensitive circuit. Yeah, it must amplify the very big signal to a reasonable signal that can be used by other block. Okay. So the next one is the mixer. So what does it mean for mixer? Mixer actually means a circuit can convert frequency. Yeah. So uh convert frequency means the frequency can be increased or to be reduced, right? If the frequency is higher, convert to be higher, it refer to a up conversion. Instead, it will be a down conversion if the frequency is lower, right? So it actually acts as a conversion block. Okay, so the third one is PLL. This is also a very hot topic when you go into the industry. Yeah. Normally for PLL engineer, the minimum requirement is 5 years. Yeah. So undergraduate course is not sufficient to make sure you can enter the interview. Yeah, if you have interest in this field. Right? So I think a master or PhD degree is helpful. Yeah. So PLL is what is a phase lock loop. Yeah. So what does uh when we use this PLL is actually a clock. Yeah, the PLL is actually a clock. Why we need a clock in our chip? So we have to synchronize the data by a clock, right? Before the data can be analyzed by the digital circuit. Yeah. So we need to have a very precisely robust clock to synchronize the incoming data. Yeah. So the specification for PLL is actually very hard to make very hard to ensure in many circumstances. So why is that? Because if we wish to synchronize a very high speed data, so the horizontal uh, movement of the clock must be limited to just tens of few femtosecond. AFS, yeah, femtosecond. Actually, this is very small. Femtosecond, very, very small. Yeah, 10 power minus 15, right? 10 power minus 15. This is very small amount. Yeah. So, which means that the PLL must generate a very clean clock to synchronize the high-speed data. Yeah. So what is the concept of high speed? So, high speed normally means the data rate higher than 100 gigabits per second. This is high speed. So what is the trend right now? The trend I think in United States already beyond maybe 800, right? Maybe 800 gigabit per second. So it's actually very high speed data rate. So the room allow for us to have noise on this PLL is rather small. So we have to design a PLL to have a very small, very, very small noise profile to ensure we can synchronize the data correctly. Yeah. So otherwise, we fail to synchronize data. The data will have increased, which mean which is referred to the bit error rate, right? The BER of the system. So this is a very critical block. Yeah, that's why sometimes industry prefer a master PhD student because they have more chance and more experience on designing this kind of circuit. Yeah. Okay, the next one is VCO. So what is that? It's a voltage control oscillator. So it's the core device in the PLL because the VCO generate the high frequency signal, which is used for synchronizing the data, right? It's actually the generation of the clock. Okay, so people will ask why we cannot just design a simple VCO. Yeah, we do not have to design PL, right? We just design VCO. So we just need a VCO to synchronize. So why we have to study? So PL, this is so difficult. Actually, the VCO is can generate high frequency data, but what is the frequency? Can you control it? It's hard to control it, right? Uh, VCO have in modern electronic device, VCO normally have very wide operating frequency. Yeah. Some talents VCO the operating frequency can vary from several gigabit, several gigahertz to tens of gigahertz. So it span a very wide frequency range of the source generation. So the PLL used to synchronize the VCO because we can use a rather low speed reference, which is a crystal reference, to synchronize the VCO and get a predefined output frequency. Yeah. So the VCO is not free running anymore in a PLL. Yeah. Without a PLL, the VCO is free running. We cannot actually control its output frequency. So we cannot synchronize any data rate. Yeah, with the PLL, we can synchronize the data rate as long as its output frequency can cover the input frequency. Okay. So so which means that we have to study source generation in VCO and also study how to control the VCO output frequency by PLL. And also we have to study how we can maintain the low noise of this specific circuit. Okay, radar and wireless connectivity are actually large system. Okay, so it cannot be done by a single person. It actually designed by a large group member. Anyway, but before interview in the industry, so we must gain some basic idea. So what is the limit of this circuit, and what is the trade-off between the performance for this circuit? Okay, the next one is power management. We have studied before, so it's about power conversion or voltage conversion. Yeah. Basically, we have the this in LDC is a LDO, right? It's a LDO and DC-DC converter, battery energy efficiency, reliability. So these are the main concern for this circuit. Yeah. So the next is a IC design and physical verification. And I think 10 years ago, people, 10 years ago, people can still work on this without a master degree, but right now I think it's somewhat difficult. The main reason is that the process right now is much more advanced than 10 years before. 10 years before, for some company, we still use the 180 micron, the CMOS technology, or I think even some company use the 65 nanometer, and the layout is somewhat easy to draw. So there are not too much rule for the IC layout. Yeah, I think all of you already know the DRC, DRC, which is a design rule check. Uh, uh, However, this situation become difficult right now because the technology now become too advanced for most of the undergraduate student. So right now in company, we have to design chips about using about below 16 nanometer maybe. Some company even using the 5 nanometer or below. So there are too many rules for us to understand right now. So it's already rather complicated for undergraduate student. Okay, so I think after this course, although this course does not cover the IC layout, but after this course, we still find a way to train ourselves with this IC layout. Yeah, it's hard to say they hire undergraduate student. Yeah, I cannot guarantee this, but this ability is quite useful. Yeah, it's very useful. Sometimes we can gain some insight from when we draw the layout. Why? Because the layout sometimes reflect the circuit symmetry and the connectivity between different blocks. Uh, how I can say is that even though you have a very good performance in the pre-layout simulation, when you join a layout, you find difficulty in connecting them. Why? This because it's actually for integrated circuit is a 2D, right? It's a 2D topology. It's not for 3D. So the connectivity is sometimes difficult than you thought when you design in pre-simulation. So this will allow you to communicate with the design engineer to think if you have other way to uh, uh, I mean, to create another schematic so that you have more flexible in connectivity between different blocks. Yeah, this is more difficult in radio frequency design because the layout plastic is very critical. I think in during if you in the future you study the master or PhD course, when you draw the layout for high frequency, I mean, uh, in radio frequency or millimeter wave, you will find the layout ultimately even truly will destroy the whole performance of your pre-layout simulation. Yeah, which means the layout is very critical. It's not something you think is just some labor, right? Some labor you don't have, you don't like to do, but it's actually very important. So it's very common that the layout engineer have to find a way to negotiate with the design engineer because there are so many trade-offs in the layout. Yeah. Okay, the next one is a test validation and application. So this is more likely to refer to the testing, right? The measurement. So after you have designed the circuit and verify them in the simulation and then tape out the circuit. In the next step, in the final step, you have to measure it. So this will test the ability of one's measurement and also how you can collect the data from the measurement. And for a beginner, so what is common is that your measurement result is quite different from your post layout simulation. Yeah, this is very common. Sometimes the measurement equipment or the environment can vary the result. Yeah, so you have to debug when this difference comes. So you must debug. So the difference come from the measurement setup or the measurement in accuracy, or you have made some mistake during the measurement. You have to find out. So this actually require you have a lot of experience on measuring different circuit. So I can share with you my experience during my PhD. During my first year, my tutor actually asked me to measure some circuit for my for the senior student. So why? One important issue is that the senior student do not have too much time for measurement. They are already close approaching the graduation. They need to focus on the paper writing, right? Paper writing or the defense of the PhD. So the tutor sometimes asks a first year student to measure for them. So during this study, we can actually study what's the response of the circuit. So why the measure results are quite different. Yeah. So normally we do not test just one circuit for one person. We test many circuit. Yeah. Some circuit have already been characterized well verified. So we will measure it again to how to say to uh to regain the data from the measurement by comparing their paper, right? Their report. So from this way, we can study if the problem comes from myself or from the chips. If the chip is not working, is my problem. Is my problem, or is the chip ju- just not working? So I must debug this. I must know the chip why it's not working and why it's so different. Yeah. So this actually need lots of time. Yeah. Also, 10 years ago, I think this is also open. This area is also open for undergraduate student. Yeah. If you like this area, also, I think you can consider this area. Okay. So the last one is the graduate research advanced study, which means you will go to a college, university to pursue the master or PhD degree. Okay. So this area sometimes require people to have creativity. Yeah. If you think you are a creative person, I think this is a good chance for you, yeah, to pursue a higher degree before going to the industry. Okay. So next we discuss the student decision matrix, which is direction fits you. Okay. So there are so many choices here. Okay. So if you are interested in math, I think you can consider algorithm. Yeah. Algorithm fits those who like math and equation. And the second one is the waveform and debugging. So what is that? Is actually the testing, right? Testing engineer. So layout, physics, geometry, and detail. So it's a layout engineer. So how about like system and application? So it's actually like it's not simply related to the analog circuit design, but I think it's more likely to refer to an embedding system or just a single chip, right? Single chip like that. Yeah, MCU. Yeah, MCU here. Okay, the next one, research and new idea. So this is actually like pursuing the higher degree. Okay, so what is the recommendation part? There are multiple recommendation parts here. Analog IC design to build a amplifier here, ADC, DAC, something like that. And verification and test, yeah, is a testing. This for layout, right? This is for the single chip or embedding system, and also pursuing a higher degree. So what are their requirement? So for analog IC design, we have to understand their spec and how this spec fight each other. Yeah. So hand analysis and hand calculation is quite useful when doing the interview. Yeah, during the interview, the expert will ask you some trade-off between each spec. So you must show them how this trade-off come and what is the limit of this circuit. The SPICE actually refer to the EDA, right? The simulation tools. For the verification is we talk about the measurement and also script. Script means we get the fault data from the measurement. We will test what's the tolerance. So what's the data? So what is the tolerance? Is the trip mode function or function well? So how different is the measure result versus the similar result? So can we recover for example, can we make the chip alive or can we recover the data, right? PVT, process voltage temperature, actually is a variation, means that the environment change, how this environment can change the performance of the chip. Uh, Actually, so which meaning that how this environment change variation can vary the circuit response. Okay, for the layout and physical design, so the first critical one is the matching. Matching refer to the matching between I mean for example for the differential circuit or fully uh identical block uh between different uh block and also the plastic, what's the plastic, the transistor plastic, and also the layout plastic, how this plastic can affect the performance of your circuit. Yeah, in high frequency circuit, the parasitic effect can reduce the gain at higher frequency. So normally we have to think about how we can reduce this parasitic effect from the layout. So if we cannot reduce sufficiently from this effect, how can we compensate this effect? And how can we cannot remove it, but we can compensate it, this parasitic effect, right? So the next is DRC LVS. I think this is fundamental, the basics for undergraduate student. Yeah, how we can run the script and how we can compare the layout and the schematic, right? So the next one is application system, and we have to collect the data sheet. So we get the spec from our customer. Yeah. So how can we optimize the whole system? Yeah. How can we reduce the system overhead, like the power consumption or the heat, right? From how we can minimize the cost of the whole system. So it's more likely to be a combination of uh, all the building block together, and it's a systematic project, right? So for this area, I think communication is quite useful. Yeah, between expert. Yeah, because sometimes you will face the limit of this application that cannot fit the requirement of our customer. So we must talk about our expert. Can we sacrifice something? For example, the area or the power consumption. Can we sacrifice this spec and we get a higher gain or higher responsivity of our circuit? So this require lots of communication between different group. Yeah. So the final one is a graduate research. Yeah, we have to learn the skill of writing a good technical paper. Technical paper normally require you have sufficient knowledge to sustain the whole structure of the paper. Normally, at the end, we have in the beginning we have the introduction to summarize what have uh, occurred during this 5 year, right? So, what is the limitation of the area you are doing research on? For example, for the amplifier, right? So, for example, for the low noise amplifier, so what is the limit of the current design approach? So why this paper, I mean the paper by other people, so why this paper cannot address well of this performance? So later you will tell the people, tell the reader, so why your approach can solve the problem without impeding without sacrifice too much of the other spec. Then in the next section, section 2 and section 3, for example, for section 2, if you give a model, not circuit, just a mathematical model or some conceptualized model to describe your why your proposed technique can address this problem and what is the limit of your proposed technique. And then you move to section 3. Section 3 will tell the reader how you build a transistor circuit based on your predefined model and what is the performance of this circuit. You can use equation to model it, and then uh, add some simulation result to support your thinking. Yeah. So section 4, you will talk about your measurement result. Yeah. For a good technical paper, the measurement result will normally fit well with the analytical and also simulation result. Yeah. So at the end, you summarize this paper. You tell the people why your proposed technique is better than other people and why other people cannot solve problem, but you can solve it. Yeah. Okay. Uh, I think that's for this slide. So next we talk about from classroom to portfolio, what student can build, right? Okay, so normally we will have some small project for each student, or during the course we will have a common project. The project will give us what is the current trend of this circuit. So what is the history? What is the history of circuit, and how people during the last 10 years, how people solve this problem? So what is the current situation of this circuit? For example, we have amplifier. So how about the historical approach to build amplifier? So this will normally give us some specification, right? For example, the bandwidth of the amplifier, input refer noise. Okay, so maybe some of you have not studied noise, but so I will go across this during our lecture. Yeah. So what is the power consumption, supply voltage, what is the limit, and also what is the temperature range that allow the circuit to operate function normally, right? So this is a spec sheet. We must have this specification before we conduct circuit. And then with this specification, we start to think about a common or a simple circuit like the differential pair, right? We first study what's the topology of this circuit that can meet the above specification. Then we do some simple hand calculation to calculate if this circuit can provide sufficient good result to meet the specification. Okay, so if the hand calculation already tell us the limit of this circuit, even the optimal performance of this circuit cannot meet the specification, we must change our mind. We must move to other topology that potentially can solve the problem, or we stack transistor, for example, to build one more stage amplifier. Yeah, before we do the next hand calculation. Okay, so in hand calculation, we normally have to buy the circuit correctly to give all the transistor have the correct operating point. For example, the current, the overdrive voltage. So what is the overdrive voltage is equal to the VGS minus VDS, right? We have already studied this in our course. And more importantly, the transconductance, because this will determine the gain directly, right? And the output resistance. The GN multiplied by RO is just simply our near DC gain of this amplifier, right? So the Heron analysis, which means that when the output vary, so what is the linear operating region of this circuit? If the output vary too large, is it possible that circuit enters some other region that that transistor is no longer operate in the saturation, right? So this is a Heron analysis because we have to amplify the signal. Yeah. Okay, so this is actually the first order estimation, which means that we have neglected the other effect of transistor. Yeah. For this kind of circuit, we actually have to think other uh, possible event like the breakdown, right? The breakdown or the linearity, and also the body effect, right? Body effect. The body effect will change the will change the threshold of this voltage we have to consider. But the hand calculation do not care about too detail of this. We just wish to know what's the limit of this circuit, and if this limit or if the spec already reached the limit of this kind of circuit, this circuit is not sufficient good to for us. So we have to think about other way, like the photocast code, right? Or other topology, right? So the simulation evidence will tell us what we should get and what we can observe from the EDA tools, like the transfer function, right? Transfer function, sometimes we will study. So what is the ability of one transistor? Normally, we refer to the response, right? The current voltage relation, right? And then when we build this circuit, we will think about the response, the high frequency response of this circuit. So what is the gain and the phase of this circuit? So why we have to start this? Yeah, because first we have to directly observe with the near this gain of the amplifier. We still have to evaluate. So what is the bandwidth of this circuit? So what is the limit of this circuit when the gain drop to zero? At this point, we still have to observe the phase of this circuit. Why is that? Because we have to see the phase margin of this circuit. We must make sure this circuit, once it has been optimized, we must make sure this circuit cannot go into the oscillation region, which is an unstable region, right? In analog design, the amplifier cannot be an oscillator. Yeah. Okay, so we can also observe other waveform like the transient. Transient is a very direct way to help us to observe the input-output waveform, right? So we have a very small input signal. For example, the millivolts or microvolts input very small, right? But we have a uh, large swing output because of the amplification. So from the transient, we can observe directly how how is the waveform relate to the input. So what is the actual amplification factor of this circuit? Actually, the transient simulation is quite useful when we design amplifier. Maybe the lecturer in the university do not tell this truth. Why? Yeah, because sometimes uh if you worry about for example, the phase margin of this transistor, you can even enlarge the gain a little bit. After that, you observe the transient without giving an input to this amplifier. If under this circumstance, if you can still observe output at this amplifier, this amplifier may have gone into the unstable region. Yeah. Because the circuit become a self-stop circuit, which means that without any input, you have a large output. So this is actually means the circuit already enter the unstable region. So the transient simulation is somewhat useful when we design amplifier to make sure the amplifier is safe, right? It's safe. Okay, so next one is the layout snapshot. Okay, the layout here is we have discussed the layout before. So the layout we have to study a lot. For example, the common century matching for designing the differential amplifier to keep the matching between the differential core. So why is that important? Because a little bit mismatch would result in the DC offset of the AD output. So this is harmful, right? Also symmetric component pairing. Yeah, so how you can how you place the two transistor, how to connect them, how to make sure the symmetry of the interconnection, right? So clean routing, short connection, and also shooting of a sensitive node. So why is that important? Yeah, because in the SoC, silicon SoC, right? We have multiple circuit block, for example, the microprocessor and also power amplifier. So these circuit are rather noisy, right? For example, the microprocessor will generate a lot of the sideband. I mean the harmonic of the beating signal. So these harmonic are actually large signal that can transmit inside the silicon chip, for example, through the interconnection, power line, and also the substrate, right? So if we do not have sufficient shielding, this harmonic will just go inside your circuit here. Yeah, just go inside the circuit here. Because this circuit is a operating amplifier, so the input here actually receive lots of harmonic from other block. Uh, so the circuit itself cannot distinguish useful in signal or harmful signal. So it amplify all the signal it can receive. So that's why we have to have sufficient shielding of the for example, the power line or the substrate shielding. Yeah, this is more specific when we have the course. Yeah, later. Yeah. Also, the next one verification report. So this is for the layout engineer, yeah,